Today in this lecture, we're going to be looking at what's called the addition rule of probability. Not today, but another day, we're also going to be looking at the multiplication rule. And basically the difference between these two is whether it uses the word and or uses the word or. So like I said, today's the addition rule. To start off with though, we got to get some vocabulary out of the way. If you're talking about whether it's an and or an or type event, both imply that there's more than one thing going on, and that's what you call a compound event. This is in contrast to the simple event where you only had one thing going on, like rolling a die. That's just one thing going on. A compound event combines two or more simple events. So they have to be simple.
Emmett Welly to the middle level office, please. Emmett Welly to the middle level office. Thank you.
All right, let's get some vocab out of the way here. If we're going to be talking about ands and ors, it means we're going to be combining probabilities of things either way. And the term compound event refers to an event that's in contrast to the last section. In the last section, we're talking about a simple event. A simple event could not be broken down any further, like rolling a die. It was just that one thing was going to be happening. But in a compound event, it's made up of combining two or more simple events. So you got the Powerball. That's a good example of that. You've got each of these is a simple event, but we're combining them to get that string of ping pong balls for the Powerball that people play. The notations. It's probability of event A or B. This is one of ours. Denotes the probability of either A or B. It shows you what it is. The other one is the probability of A and B. And how we calculate these are going to be different. Today we're going to be looking at this one. In the next lecture we're going to be looking at this one. It's the probability of A and B occur in the same trial. I'm trying to remember that for the next one. It's got to be in the same trial. Or A in one trial and B occurring in a second. So the probability of A and B depends on the context, which makes it a little bit hard to imagine. But actually when you start doing it, it pretty much kind of explains itself typically when you're going through with them. Another vocab thing we have to talk about before we start combining is the term mutually exclusive, because some things are mutually exclusive and other things are not. When two events cannot happen at the same time, we say they're mutually exclusive. So for example, flipping a coin, a head or tail, passing a class and failing a class at the same time. Now, excuse me, what I meant back here, I should have added the word and. Head and tail. You can't get a heads and a tail at the same time. So scratch or, put the word and in there. That's just not going to happen. You can't get them both at the same time. You can't be passing and failing a class at the same time. You can't be standing up and sitting at the same time, at least not that I can imagine. Let's look at some real basic ones. These are what you call addition problems in a situation where they are mutually exclusive. Okay, so this example here, and I'm really simplifying something here. Let's say that you got a snowmobile dealership that decides to select a month for its annual sale. What I mean by I'm simplifying, this is not the way a snowmobile dealership would actually work. There's going to be certain months that they'll want to have their sale in. We're just ignoring that right now. Let's just say that you just picked at random out of the entire year. Find the probability that it would be in April or October. Notice the word or. Now let's just think of this just instinctually. Okay, there's 12 months out of the year. There's 2 months here, so probability should say, reality should say, well, it's 2 of the 12 months, so 2 out of 12. Our mathematical calculations have to match our reality. The reality here is the answer should be 2 out of 12. All we got to do is make the mathematics match it, because the problem becomes I have for April, that's 1 out of 12. For October, that's 1 out of 12. Am I going to add those fractions together, or am I going to multiply those fractions together? And the truth is, I know the answer is 2 out of 12, and the only way to get that would be is if I added them. And that, in short, is going to be your addition rule. If they're mutually exclusive, and the word or is there, you're simply going to add the probabilities. Now, I'll get to in a couple of minutes what if they're not mutually exclusive. But if they are, you just simply add the probabilities. Here's another one. I would like you to try it. There's a Halloween box of candy that has it has 7 little bags of M&Ms, 10 Reese's peanut butter cups, 15 Starburst, 16 almond joy. Nobody likes those. 9 Crunch, 5 Skittles. Bags of Skittles, we'll put it that way. Find the probability that if you reach in and grab one, that it's a Crunch bar, or that it's a bag of M&Ms. Those little bag of M&Ms like right there. So why don't you pause this and give it a try. All right, so we've got an OR situation. We know we got to add the probabilities, which means first you got to figure out what are the probabilities. So Crunch bars, well, there was 9 of them out of the total, so you do have to count how many there are. And then M&Ms, there was 7 of them out of the total. So the probabilities, there was 52 total here, so you had to add them all up together. Probability of a Crunch is 9 out of 52, M&Ms 7 out of 52. What's really nice here is they have a common denominator. It's not always that nice, so I'm going to remind you right now that if you are ever finding probabilities and they have different denominators, with addition you do have to get a common denominator before you add them. I didn't have to do that here, but that will happen. Trust me. All right, what if they're not mutually exclusive? So I'm going to give you an example of one here. Before I do that, I need to remind, most students understand a deck of cards, but it never fails. I've got 1 or 2 in class that have never really played with decks of cards and don't really understand what I'm talking about, so I want to explain. In a deck of standard cards, there's 52 cards. There are 4 suits is what they're called. They have little markings on them. There's hearts, there's spades, there's clubs, and there's diamonds. So that's the 4 suits in each suit. It goes from ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, which is 13 cards in each suit. So now I can ask a question. What's the probability of, out of a well-shuffled deck, we'll put it that way, that you randomly pull out a heart or a king? All right, there's that. But this is not mutually exclusive, because there is one king that is a heart. And that's what I'm showing you here. So here's the 13 hearts. And here's the 4 kings. Each suit has a king, so there's 4 of them. But the problem is, right there, that falls into both categories. So this is not mutually exclusive. Let's just take a look at it. So it would be these plus these, but the problem is right here, this king of hearts is getting double counted. We don't want to double count, so we need to get rid of at least one of them. In short, we need to subtract back to here. I'm going to refer to this as the overlap. We will subtract the overlap, and then that way we're not double counting. So we're going to subtract one of those back out, which is what the overlap represents. And we end up with this. We would have, okay, well, there's 13 out of 52 hearts. There's 4 out of 52 kings. We subtract the 1 king of hearts that's overlapping. Nice enough, I still have a common denominator here, so I can just simply deal with the numerator. And the probability would be 16/52 of getting from a randomized deck a heart or a king. And that's when it's not mutually exclusive. Okay, so let me kind of quick summarize this. The addition rule, which is when you see the word or. Anytime it's or, you are going to be adding probabilities. That's a horrible little star. What should be a star there? Anyways, if P and B equals 0, in other words, they're mutually exclusive. They're mutually exclusive. I'll just leave it at that. Events, and you've got the probability of the 2 of them. This would be like the snowmobiles or the candy bars. Well, then you just simply add them together. And that's what this is saying. then the probability of A or B equals the probability of A added to the probability of B. But if there's overlap, like with the cards, then they're not mutually exclusive. So there's this overlapping part here. What you're going to do is you're going to take the probability of each thing. You're going to add them together, but then you'll subtract out the overlap. And that's what this is saying right here. The and is the overlap. So if it's probability of A or B and they're not mutually exclusive, you take the probability of the first plus the probability of the second, but you subtract out the probability of A and B. Or, like I said, I like to describe that just as the overlap. It's an easier way to think about it. Okay, so let's just practice this. Couple real simple ones. These you could probably figure out by just counting quick using the sample space, but it'll demonstrate the rules here. Okay, so I'm gonna, with just one die, I'm gonna roll. And what's the probability of getting an even number or a 2? Well, notice that 2 is an even number. Okay, so we've got some overlap going on here. And so what you're going to do is you're going to do the probability of getting a 2, which is, of course, just 1 out of 6. The probability of getting an even, well, it'd be 3 even numbers, so 3 out of 6. So you're just going to have 3/6 plus 1/6 minus the overlap, which is 1/6, which brings us right back to 3/6, which I'm going to say is a half. So that'd be 50-50 of getting an even or a 2. Which, of course, is kind of a silly question, but I'm trying to show you one that, like I said, you could probably figure out without using the formula. They will get more complicated, so I'm trying to get you to figure it out with easy stuff before we move on. Little bit more complicated, but not much. The probability of getting an odd number or a 2, which here they're not mutually exclusive, so you'll just simply add the two probabilities together. 3/6 plus 1/6 is 4/6, which you always want to reduce your probabilities when you can, so that reduces down to 2/3. Okay, let's look at something that's not as simple, something that you can't just probably easily count in your head. Let's say that there's 75% of the University of Minnesota undergraduates live off campus. By the way, these were true statistics probably 10 years ago. I haven't looked this up in quite a while, but this was originally stuff I did look up. With 23% of freshmen living off campus, so the rest of them are on campus in dorms, and assume 30% of the students are freshmen. And you might question that, why 30%? You got to remember attrition rates. Not everybody that starts out college ends college. There's going to be people that drop out, that don't make it. In fact, attrition rates are higher than what you probably think. So it's not 25% for each class. You might be thinking, well, freshman, sophomore, junior, senior, that should be 25%. That's not true. There's more freshmen typically on campus than any of the other grades. So that's what we're going to use right there. If a student is selected at random, what is the probability that that U student lives off campus or they're a freshman? Oh, so we've got an or situation. We're going to have to add the probabilities and then subtract the overlap. So what we're going to look at here is the probability of commutes or a freshman is 75% plus 30% minus the overlap, the 23%, because they are freshmen and live off campus, which gives us 82%. All right, that is it for today. There's some problems to practice right there. Please do your practicing. Have a good day.